English mode. So let's discuss this place where we changed it a little bit last time, but first, okay. So the beginning of the RAM complex. So let me discuss one more time. So the RAM complex. So the beginning that I presented, like for the first time, was actually correct. So I have 0 going, just 0 map to omega 0 of m, and then we just proceed. Anyway, so the question is, what is H0 of m, right? And the answer is that these are all locally constant functions. So vector space. Like this. So vector space of locally constant functions. So the derivative should be 0, right? Since it's in the kernel of D. Okay, so we are fixing it like that, and this should be correct. Okay, and last time we stopped at homotopy equivalence of the RAM homology. For that, I also need to clarify a few things. So if I have just so let me recall what is homotopic maps. So suppose that I have F and G, they are two maps, and for homotopic maps, I don't even need M and N to be smooth manifolds. I just can start with topological spaces. So this is topological space, and this is topological space. And then I have two continuous maps. And then we say that we have homotopy between these two maps, so H. It's from where to where? It's from M cross I to M cross I. So this is homotopy between F and G. So if, well, so I here is just an interval from 0 to 1, closed interval. If what? H is continuous, and we have that H of P0 is F, and H of P1 is G. So this is just homotopy, and we say that the two continuous maps are homotopic. Okay, if homotopy exists, then we call F and G homotopic. and write it like that. Okay. But then we can, add some structure and say that, okay, let M and N be smooth manifolds now. So if M and N are smooth manifolds, I can actually take F and G to be smooth maps. Then again, they can be homotopic in usual topological space sense, and then I write such a symbol. But they can also be homotopic via smooth homotopy, right? And this is like a more strong condition. So if F and G homotopic via smooth homotopy, well, here I set interval. This is not really a manifold. It's a manifold with boundaries, right? Which is a little bit different thing, not too much different. Well, I can say, I can consider, what does it mean, smooth homotopy? Okay, it means that I have now H. Well, I can say like that, from M cross R to M cross R, right? So there exists H. And this is smooth such that, again, this HP0 is F and HP of P. And here also, right? It's a right of P. And HP1 is G of P. So it's enough for me to be smooth, like a little, like it can be continued smoothly outside of interval. Then I'm saying that it's smooth on interval. Okay, but we'll discuss a little bit manifolds with boundaries. We'll need them, at least for Stokes' theorem. Okay, and then we say that F and G are smoothly homotopic. Smoothly homotopic. And we write, okay, such a symbol, okay, just to distinguish. And then the proposition that was formulated last time is that suppose that I have two maps, F and G. They are from M to N, so these are smooth maps within smooth manifolds. Smooth. Then and suppose that they are smoothly homotopic. Then F star equals to G stars, where these are maps on homology, on H dot 0. Okay, so okay, let us see like a idea of proof of this. Well, usually when you try to prove that two maps induce the same map on homology, right? You build, well, there's a standard construction. So first of all, let me let me introduce this map I, T. Okay, so this map is, so this is proof. So this map from M to where? To M cross R. Yeah, by the way, what? I don't even need yes. So here something is not really well, right? This should be to where? To so my f is from m to n, right? And g is from m to n. So here I should write n, right? So this is one thing. Let's correct it. And here as well. Where was it? Well, just all right. So now it's better. So okay, so I have IT, which is from M to M cross R, and this just sends point Q to it's just inclusion, but it includes it into just like that. Right, so T is just a number, real number. Fine. Then F star is just composition of I star 0 with H star. And G star is just a composition of I1 star with H star. Here, H star. Right? So, and I want to prove that this equals to this. So I would like to prove that actually I0 star equals to I1 star. So this is my goal. Right. So for that, there's usual trick. I would like to wall to construct map H. This map from where? From omega k on M cross R to omega k minus 1. I guess M. Such that d of H omega plus H of d omega would be the difference between I1 star omega and I0 star omega. So this is for any omega from, so this is a form on where? M cross R. Well, guess k here should be. Right. So for any k, so go for any k to build such a map. Then we are done, right or wrong? Because if I take omega from right, if I take omega from the cocycle, right, then this is gone, the omega is 0, right? And then therefore modular boundaries, then this is 0, right? So then we are done. Since if omega is inside kernel of D, then, well, the class of I1 star omega minus I0 star omega is 0. Because what is left is boundary. Okay? Alright, so how to construct such a map?
Excuse me, is it supposed that the leftmost term is 0? Or we should also prove
It's not it's not 0 in as a form, but it is 0 when we consider its projection to homology. And homology is kernel quotient by image. Right, so I have to take something from kernel
yeah.
and quotient by image. So this is in the image. All right, yeah. So I just take right. So inside R. So let me just give H to you, and then we'll check that this actually satisfied this line. But first, let me introduce a vector V. So this is from vector fields on M cross R, and this is just, so if we have like a variable here T, right? Well, this is real numbers. Then this is just D over dt. It's just notation. I mean, what should I write? Should write this. V equals, so V is inside here, and V is just D over dt. Okay, and I just define H omega to be an integral from 0 to 1. So what should I do? I should take omega, and so this is from, omega is from here, then it can, I can plug inside this entry V, so I substitute V. Then I pull it back by I star T. Right, but I star T it's not so great, is it? So let's see. So, right, sorry. Still something is bad, because, and then So I integrate with respect to t. No, I don't like it, so let me fix this real quick. So if I take omega, omega is inside here. So if I yes. Well, I can just, I guess, okay, I can just erase this, right? Because then this becomes like a function of t, right? And I can integrate, right? So yeah, so what does it mean? I am taking omega from here, omega from here, from omega k of m cross r, right? So omega has, well, it can eat like two vectors. One vector, I don't know, let's call it w, and the other one like v. So v is from here, and w is from here. So basically, v substitute omega, right, is actually omega dot v. So that's what it is.
And there are two, they differ from each other by the position of v, right? One is one puts v in the beginning, another v in the end.
Yeah, like the hammer.
Yes, sorry, say it again.
We can write from left to right and from right to left.
Ah.
There are two operators, right? And they differ just by the position of v.
No, it's just, well, I don't know. I don't. So in the homework was the other symbol.
And it puts v on the first position.
No, that was not my intention, but it's okay. Let's maybe keep the same symbol, okay? It's just, no, we cannot put v, since v is a vector in here, we cannot put it in the first entry, right? So it's just, it's clear where should I substitute, but okay, let's keep the same symbol. Right. And then what I have is that right. So this now becomes a function of t, right? So this becomes a so this depends on t, right?
We took v from r, where t lives.
Yes. So v is just d over dt.
Yes.
So it's some form where it has like something like wedge dt. So something here times some coefficient. And so we substitute, we just evaluate this on d over dt. That's what happened, basically. All right?
Why do you say that it depends on t?
Well, because this coefficient depends on t somehow. So this is a function depends on t. So now we get, so this is kind of evaluation, so I substitute t, this is just 1, right? And what I get, well, where I don't have dt, like locally, right? Locally, it's clear what it means. Where I don't have dt, it's just these terms are gone. And where I do have dt, this becomes 1. I have something left in here, which is k, k minus 1 form on m, right? Because it was k form in here, minus 1 because this goes to 1. So what I get here is actually, so this is t valued k minus 1 form on m.
How do you integrate it?
Well, it's just a vector space, right? So you, well, you basically, well, it's vectors. So you decompose it in some basis, right? And integrate each coefficient. Yeah. So that's how it's done. So and indeed, then we get, so when I integrate, it does not depend on t anymore, right? And I get just k minus 1 form on m, the way I wanted it. So h goes from here to here, right?
This is how you find action of h on form omega, right?
Yes. Yes. So that's the definition of h. So now we need to check this. Okay. So let's do this. Okay, let me write. So we need to compute this d h omega plus h d omega, right? So this is what I integrate. So integral is I integrate, and so I can put actually d inside integral, right? Because d is so let's see. So it will be d. Well, because d is linear, and that's why, right? So then I will have d, and then v, again, another symbol, this one, omega, plus v, d omega. And then I take this and integrate with respect to t. But then I use what's called Cartan's magic formula, like a simplified version of which you checked at home, where m is another copy of r. But for like you just for proof for any m is just the same, just the idea is the same, and you know, consolation that you'll have there is the same. Just technically you have more terms, and that's it. So let me just right. So I will have d over ds. So this integral from 0 to 1, d over ds, theta s star. Well, at s equals to 0. Well, I need to first apply, so I need to do it more accurately. So I need to do it like this. I need first to apply theta s to omega. So I need to write what is theta s as well, but then take derivative with respect to s, and then take x equals to 0. So this is still function of t, so I can integrate with respect to t. And then theta here is just, well, it is function from where to where? From n cross r to n cross r. And it just takes a point P and PT, and then it just shifts, so I need theta s. So it just shifts this entry, P of t plus s. Okay? But then, so this is Cartan's magic formula. Magic happens when things cancel there in this sum. So Cartan's magic formula. And then this is the same as integral from 0 to 1. Well, I take theta, right, and apply it. So this is actually the same as pull-backing theta t star omega, right? And then taking derivative with respect to t. Because what do I do? I am at the point t, right? I shift. Well, so how derivative at how do I do derivative at t? I shift by s and consider a limit and put s equals to 0. So consider limit s equals to 0. So this is really derivative at t then. So then like that. Well, it's an integral of a derivative. So therefore it will be just what? Right, but this is, yeah, so theta star 0, well, at 1, of omega, sorry, of omega, minus theta star 0 of omega. But this is actually the same. Well, we need to get actually I1 star of omega minus I0 star of omega. But this is actually the same thing because, well, so basically I0 from I from theta, so with star, just difference only by how I look at it. Theta actually thinks of this as a variable, and I thinks of this as a parameter. That's it. There's no really difference between them. Right. So when I fix this parameter, it just erases this, and this becomes yeah, IT. So then I fix this parameter. Yes. Okay. Is it clear, or should I? explain more. Anyways, so you can ask questions, or you can ask questions afterwards if you wish. So anyways, so we get we get what we wanted. If we look closely at what happened, but then yeah. So basically this is it. So we proved this smooth homotopy equivalence. But then, well, let me formulate something which we will not prove because it will take too much time, which is called Whitney approximation. I'm just going to use it. So Whitney approximation. Theorem which just says that any continuous map is homotopic to a smooth map. It's a very strong theorem, but it becomes very handy, but you need like a whole lot of theory to prove it.
Not on anything.
Yes. Well, you start with manifolds, smooth manifolds. You have just a smooth map, just continuous map. Then it's homotopic to a smooth map. And moreover, if so, maybe let me be specific. So map F M N is homotopic to a smooth map, and let me denote this map somehow. G. So moreover, if F was smooth on some submanifold, A inside M, then we can find G, this smooth map, such that they just coincide on A. Okay. So now we're just going to apply it and formulate Poincaré lemma. Which says that suppose that I have homotopic manifolds M and N, then their Dirac homologies are isomorphic. Well, just coincide. TR M equals to H TR N. Okay, I need to maybe explain what this is. So I have two manifolds, right? What does it mean? The homotopy, homotopic or homotopy equivalent. So definition: M and N are homotopic or homotopy equivalent if well, there exists continuous maps which ones f from m to n and g from n to n such that if I compose f with g, this is homotopy equivalent to identity on where first apply g and then f, so on n. And similarly, if I apply first f and then g, f and then g, this is homotopy to identity on n. Okay. All right. Well, we already have everything, and we just use Whitney theorem, so it's very easy to prove this one. So proof of theorem. So I have two continuous maps, right? So just keeping this notation, right? I have f and g like that, so they're continuous. And then by Whitney approximation theorem, so we'll apply it 2 times. We have smooth maps. F tilde, and F tilde is from M to N. G tilde is from N to N. Well, such that F is homotopic to F tilde and G is homotopic to G tilde. This is just by Whitney approximation theorem. Then I have that we compose F tilde with G tilde. So composition is of course homotopic to just composition of F and G without tildes. Right? And I know that this is homotopic to identity on M. Right? And similar to that, similarly, we have that the G tilde composed with F tilde is homotopic to identity on M. Therefore, okay, we have homotopy, some homotopy from this map to this map, but again, I can now apply Whitney approximation theorem again. So homotopy itself is a continuous map, right? And I can consider a smooth map, which is homotopic to homotopy, right? And which is coincides, which is already smooth at the points of interval. Right, so I have a homotopy between F tilde and G tilde, they're already smooth, right? So I can apply Whitney approximation theorem where A is just consists of just points of intervals times M. Okay, and so actually I can find smooth homotopy. And here. So ID on smooth. Applying Whitney approximation theorem, so let me abbreviate it like this. Again. But this means that F tilde star is an isomorphism between the ramp homologies, right? Because it has inverse, which is G tilde star. This is by smooth invariance, smooth homotopy invariance that we proved. So therefore, F tilde star is an isomorphism between H d ram of M and H d ram of M. And I mean isomorphism, so I need to be specific, so these are some vector spaces, but I really need this to be isomorphism as graded vector spaces, meaning that each degree, like kth homology here is isomorphic to kth homology here. It's not just so isomorphism as graded spaces. Yes, graded spaces. With F tilde star inverse is G tilde star. Okay. All right. So this is it about homotopy equivalence. So of the RAM homology. So in particular, we know. Well, we can compute the RAM homology of a point, and everything which is contractible to a point has the same RAM homology. Sometimes people call this Poincare lemma. Well, it's just a consequence of what we proved. Okay, so now let me talk about. So I'm moving towards integration, something that I guess would be not good not to discuss. So anyway, so let's start with. So I would like to define what is an orientation on manifold. But first, let me start with just vector space. So suppose that I have vector space. And suppose that I have B, like B, Gothic B, is a set of all bases of then I would like to introduce equivalence relation on B. So suppose that I have two bases, B1 and B2. So these are elements of B. Then we define that B1 is equivalent to B2 if and only if B1 can be obtained from B2 by some linear transformation such that its determinant of this transformation is greater than 0.
Can I give an example?
Yes, I can. R2, R1, you have two orientations. All bases such that the arrow looks to the right, and all bases such that the arrow looks to the left. To transform one basis to another, if the arrows look to in the same direction, you multiply by a positive number.
The bases are just the families of open sets on B.
Basis to basis.
Да.
Bases.
Да, это пока только заготовка для векторных пространств.
Все, я просто подумал, что это база, как
Не-не-не. Да. Okay. No, that's much simpler. And then, well, this equivalence relation, easy to check. But then I say that orientation on B is the same as the choice of equivalence class. With respect to this equivalence relation. Right? And then I say that orientation on a smooth manifold M is a choice of orientation on TPM for each P, but they should be consistent in the following way, so such that for each point there exists an open subset, open neighborhood of this point, and a bunch of vector fields on U. So V1, blah, 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 Dn. Well, n is the dimension of m. So these are vector fields on U. Okay. Such that for any y from U, V1 evaluated at y, so this will be tangent vectors, V2 evaluated at y, Vn evaluated at y. So this forms, so this is a linear independent set, so this is forms a basis of T y u, and yeah, so I need to introduce some notation. So orientation of smooth manifold M is a choice of orientation on TPM. So let me denote this choice for each P as OP. Maybe this is not the best. If anybody knows anything about shifts, usually always a shift, but okay, we don't mess with this here. So O stands for orientation, rather. So on each TPM I choose class of equivalence on the set of bases for TPM and call it OP, right? Such that these all OPs for each P are consistent, meaning that locally around each point I have a n linearly independent vector fields, right, such that v1 y vn y. So I want this is a basis, and I want to consider class of this basis, and this is O y. So this is what is an orientation. Well, sometimes it exists, sometimes it does not exist. But when it does exist, we say that, okay, I'm showing my manifold M. So M is orientable if orientation exists. Question to the audience: how many orientations can I have on a manifold? Okay. Any other? Everybody agrees.
If it's connected.
If it's connected to, yeah. But if it's not, then what? Actually, 2 to the power 2.
Power of connected.
Power of connected components, right? Not the power. Yeah, 2 to the power connected components, yes. All right. Very good. So next thing that I need is, so I would like, my goal is then to define integration on the manifold. So for that I need a partition of unity. And right, so let me start with let me start with some atlas. So again, I have some smooth manifold. I start with it, and then I have a smooth atlas on it. UI. Well, I don't even need, I guess. It to be atlas for now, but okay, so it will be eventually. So let us fix let us fix an atlas. So this is smooth atlas.
May I ask a question?
Sure.
The previous part. We defined the rotation. We talked about the positiveness of determinant. Where is the positiveness of determinant in this в этом суждении? Где-то оно есть?
Ну, в этом определении. Тут главное, что, ну как, вы не перескочите через ноль. Главное, что вы, если у вас есть базис из векторных полей гладких, вот, они все линейно независимы, вот, то есть, ну, вам, чтобы перескочить на другую ориентацию, вам надо, вам надо, чтобы ваш в какой-то точке, вот идут, чтобы в какой-то точке, они просто, они стали линейно зависимы. Да, просто, как?
Я, может, наверное, не понимаю.
Сейчас.
Верхнюю строчку. Вот справа на правой доске.
Хорошо, давайте поймем, что...
Мы взяли тут наш базис в какой-то конкретной карте точки Y, реализующей. И...
я просто говорю, что у меня есть... То есть я знаю, что у меня есть два выбора на каждом, значит, в каждой точке, да, у меня есть касательное пространство, да, и у меня есть два выбора ориентации.
Да.
Вот. Там можно на самом деле это определять, у меня здесь есть какие-то вектора, вот, а последний я могу либо вверх, чтобы смотрел, либо вниз. Вот. Как-то так можно про это думать. Вот. Это соответствует двум разным ориентациям. Пока я последний не определю, в какую он сторону смотрит. Вот. Да. Нет, я выбираю, значит, мою ориентацию на каждом в каждой точке. Вот. И я говорю, что на самом деле моя ориентация может быть задана просто гладким векторным полем. То есть я не могу взять и вот у меня здесь ориентация такая, а потом резко на бац изменилась. Вот, потому что, или даже вот на R, давайте, легче всего на R, наверное, думать. Вот я в каждой точке выбираю, на самом деле, куда у меня смотрит вектор. Вот. И, значит, я говорю, что локально вокруг точки у меня, куда смотрит вектор, задается гладким, невырожденным векторным полем. Вот. Это значит, что, у меня... Чтобы поле было гладким, они все должны смотреть в одну сторону, вокруг этой точки. Потому что чтобы она смотрела в другую сторону, у меня поле идет, и чтобы он развернулся гладко, он должен обнулиться. Но такое не может быть, потому что я говорю, что у меня поле не вырождено. Вот это значит, что у меня ориентация локально вокруг, в R, вот они все в одну сторону смотрят.
Можете вслух произнести, что значит это уравнение сверху?
А вот это значит, что, давайте проговорим. Это просто, у меня есть базис.
Да.
И этот базис, я беру класс, соответствующий вот этому представителю. Вот. И он совпадает с тем классом, который я выбрал заранее. То есть, что такое?
Все, да. А вот это ваше суждение можно формализовать каким-нибудь требованием на то, что мы из одних координат в другие переходим, но с каким-то переход тоже какого-нибудь происходит?
Да, можно так.
Тогда оно и есть,
да? Можно по-разному определять. Вот.
Спасибо.
Так, хорошо. Okay, so we have this. What is this? yes, so this is my setup actually. So I have this. I'm already kind of starting to define what is an integration over top form on M. And moreover, I would like some more conditions. So this is a smooth atlas, but it is what is called locally finite. Right. So so atlas. So this is such that for any I, well, well, right. Yes. So maybe. So first of all, I want just for convenience, I want any image phi I of ui to be, so this is in some Rn, right? So I would like it to be just an open cube of n. I can actually, require this. This will make just technically my life easier. All right, and also also let me fix. So I'm fixing M, and I'm fixing omega. So this is a differential form, but it's what's called top form. So this is from omega n of M, where n is a dimension of M. Also, I would like that support. So I would like this form to be of compact support. So omega has compact support. So let me write it like that. Support of omega is compact. And also there exists some finite set. J from, well, this runs over I, like that. Such that, well, support of omega right? So it actually means that, so support of omega is compact, and of course this is a cover, right? Or UI is a cover of this support, so therefore there exists finite set J such that support of omega is inside, so this is finite subcover. I over J UI. Okay, So what else do I need? So also I would like to have partition of unity subordinate to ui. So let psi I psi I. Let me So here I actually would like my I to run over J, right? So psi I is I runs over J, so this is partition of unity subordinate to this cover ui is I of I runs over I runs over J. So this is the cover. So what we care about is only about cover of support of omega. Okay, so I want so I fix manifold M. I fix top form. So top form meaning it's n form where n is dimension of M, and I want support of omega to be compact. So then suppose that I have smooth atlas. Since support of omega is compact, I can find the finite subcover of the support of omega. Okay, and so that I denote by J. But then I also would like to fix partition of unity subordinate to this cover of the support of omega. What does that mean? This means the following. That is, first of all, well, each psi I here, these are smooth functions on M, such that the following things satisfied. First of all, the value of psi I is between 0 and 1. Second of all, support of each psi I is inside ui. And 3 is that the value of psi I as I runs over J is is just 1. And this is for each point. This is for each point in where? Well, in this cover, right? Union I over J ui. Okay, so how to construct such thing? Well, it's actually not so hard. So first, let me check that I actually listed all the properties. Yes, I did. Okay, so how to construct such thing? So existence of psi I. So first I just need to fix some fi's, right? So start with fi's from C infinity of M.
we're still living in the support of omega.
Yes, we do. So each support of psi I is inside UI.
Нет, тут спорт омега ни при чем вообще.
Ну, саппорт омега тут, значит, ну, мы живем в конечном под покрытии, значит, саппорта омега. Вот. Это
Я
все.
просто не понимаю, при чем тут омега, она похожа будет использовать?
Ну, что мы хотим? Мы хотим определить интеграл по омеге, по нашему m.
Все, понял.
Вот.
Да,
Но для этого я сейчас что-то технически пытаюсь крутиться. Вот. Ну и вообще хорошо интеграл определяется для омега с компактным саппортом. Вот. Ну просто потому, что это будет какая-то там сумма конечная. Вот. Я хочу локально определить, а потом у меня будет как бы конечная сумма. Вот.
Ну, нам не должна стоять.
Что?
Мы же можем взять, ну, в смысле, если она, допустим, сейчас, я не уверен, что так может быть, потому что глупый говорю, но если она у нас, допустим, в случае R ограниченная, но не замкнутая, уже может быть чуть побольше и замкнутая. Или просто такого не бывает, потому что там что-нибудь из непрерывности бывает. Нет, но условия...
Можно, в принципе, да, там можно. Это надо смотреть, мне кажется, по...
Ну ладно, если это так, в сторону, то...
Ну, значит, на R, мне кажется, нет никаких проблем, но значит, да, ну не знаю. Просто, не знаю. Может быть, можно, но мне кажется, что ну, давайте посмотрим позже. Давайте, значит, запомним, что... Так, ну хорошо, значит, okay, so we need to switch to English. So how to construct such psi I? So first I start with some functions, just some functions fi, such that they are greater or equal than 0, and then also support of fi is inside ui for each I. And then, well, you also would like that sum over I fi is not 0 for any, so this is at p, so for any p from this cover, then actually, well, such things you have a lot of choices how to do that. And then psi I you just define as fi, right, divided by the sum divided by the sum fi, and here I'll over j, to satisfy this property. And then that's how you construct this psi. Okay, so let's go to the definition. So now also we need orientation. So suppose that M is orientable and we pick an orientation. So is oriented. With orientation, so denoted as before, OP, SP runs over points, SP runs over all points in M. Okay. And then, so suppose that I have, take my omega, so now I define some local integrals. So I take omega and restrict it to ui, for each ui like that. And suppose that is just given by one function really, because omega n is one-dimensional, locally it's one-dimensional over C infinity of u. So like that. So this is some function, omega I. So this is from C infinity of ui. It's just definition of omega I. Then we define well, I need to define some number which I will denote AI. So this is some sign which I will describe a little bit later. Then integral, like multiple integral from 0 to 1. And then I should have to write psi I of phi I inverse of x. Then omega I of phi I inverse of x. And then dx1, dxn. So this is one piece from which we pull the whole integral together. Okay, but what is this epsilon I? So epsilon I, by definition, is either 0 or 1, 0, if, well, I have d over dxi at each point e, right? And so locally, so this gives me locally basis on ui, right? And so this at each point, and so it can be inside OP, so it can be equal to OP. And then epsilon I define to be 0. Or it can be not OP, and then I define epsilon I to be 1. Okay? Again, this is a lot of brackets. Is it clear? So this is a basis, and then I take class of this basis. And this is this class, exactly the class which is coming from the choice of orientation. Anyway, so d over dxi at point P is oriented positively. All right. Then I just define the following number. Integral over m of omega is sum over ai f from J. So these are some numbers, and I can sum them with this finite sum. Okay. One thing we should worry a little bit is that it does depend on the choice of cover, right? Or other things that we fixed, psi I, for example. like a partition of unity. And the claim is that it does not depend, of course, on all these things. So integral over m omega does not depend on, well, on atlas, on psi I. What else? That's it. That's the only thing that we chose. I don't know. Do we want to check that? So check is not really straightforward. There is some trick. Well, maybe let me not check it like completely. Just write a couple of lines. So basically, I can first take my integral over omega, right? And first I can write this as a sum over I from j of psi I omega integral of this. Well, we need to check that integral respects addition, which is clear. And so therefore, if I have I can write psi omega as a sum of psi I omega. And then consider this. So if I'm using atlas A and atlas, so I'm comparing two definitions, one with this data and another one with another data. So you start with some other atlas A prime and use like partition psi prime, everything with primes, ui prime, phi I prime, blah blah blah. So you're comparing these two things, but then you need to take this guy and treat it using the dashed data, the dashed definition, right? So it will be sum over I from j and j from j prime. So j prime is j corresponding to this prime stuff that we fixed, the other choice of all this data. Integral, and then I have this numbers ai, right? So ai corresponding to a form, I will write ai, so maybe let me write it like this, right? So I take this guy, right, and write aj corresponding to psi I omega, but with this data. So I would denote it, I don't know, somehow with prime. It means that I take this form and use primed psi and phi and x's to define this number. On the other hand, I can do the same and start with decomposition in j primes, integral over m psi j prime omega, and then I will have sum over I from j and j from j prime, and then I will have, well, I don't have integral here, sorry. And here I have what? A without prime, so but I need prime in here, psi j prime omega I. So I need to compare these two things, which are just the integrals, you know, multidimensional calculus. And you can check that then I psi j prime omega is equal to j psi I prime here, omega, this is just change of variable for the formula. So change of variable of integration inside integral. You can check it, let's not write it. So check change of variable formula. And so therefore, here we treat this integral using definition using this initial data, and here using this initial data. And so at the end, they just coincide. And so that's why the claim is true. Okay, is it clear what happened? Only one person reacted. Okay, everybody else is just for seminar here, I guess. So, okay, so I guess if no questions, then let's continue. Right.
I believe our time is up.
Is it? So we start with 10, and then we need to finish at 11:30, right?
11:20 actually.
20, sorry. Okay. Let's break.